All right, in this inquiry, we're trying to determine the gravitational constant, see how close we can get it to C to be 9.81. And the way we're going to do this is we're going to be dropping objects from a known distance, and we're going to measure how much time it takes for it to fall. And we can use an equation to do that. The droplets, or the things that we're going to be dropping, are going to be little water droplets. And we have this burette here, and we can open up the valve right there, and we can start dropping water droplets down this distance to hit this aluminum foil. And we want to measure how much time it takes for one drop to fall from this burette down to the aluminum foil. And then we're going to put that time into our equation and figure out what the gravitational constant is. So the distance that we're going to drop, we're going to measure also. And I have this set up so I put this exactly 1 meter above the aluminum foil so that objects are going to drop down 1 meter. So the equation that we're going to use, hopefully by now maybe you're starting to know all the equations, is going to be displacement equals the initial velocity times the time plus 1/2 acceleration. Now in this case, the acceleration is actually gravity. We know that gravity is the acceleration rate, so I'm going to put g instead of a in there, times t squared. Now you'll know that these water droplets here are falling with an initial velocity of 0, so that first term, the VIT part, will be able to go away. So now I'm left with d equals 1/2 times g times t squared. Now we're trying to determine what g is, so we want to solve this for gravity. So that would be gravity would equal, take 2 times the other side, so 2 times d, and then divide by the t squared. So I'm going to do this. So we actually know what the displacement is. We're going to drop these water droplets 1 meter. So I like to do that. That way that makes the math even easier. Now the gravity is just going to be 2 over the time squared. So all I need to do to figure out gravity in this experiment is to measure how much time it takes for a droplet of water to fall from here down to there. So the tricky part is, how do you measure that fairly precisely? That would be kind of difficult. I could open a stopwatch and try to let a droplet fall and try to start it right when it falls and then turn the stopwatch off right when it hits the aluminum foil, but that's going to be pretty quick, and I don't know if our reaction time is that good. So what we're going to do instead is we're going to use your knowledge about frequency and period. The frequency of something happening at nice regular intervals, the frequency is equal to 1 over the period of time that it takes for one event to happen. So what we're going to try to do is we're going to open up this valve here so that we start getting droplets of water, and they're just dripping one after the other, okay, at a certain rate, a certain frequency rate. Now, what do we want that frequency rate to be? We want that frequency rate to be fast enough so that when one drop hits the aluminum foil, and that's why I have aluminum foil there, because you're going to be able to hear the sound. When you have a drop hitting the aluminum foil, the very next drop needs to just be falling. That way, the time that it takes for a drop to fall will be the amount of time you hear between aluminum drop taps on the aluminum foil. So we have one drop here, and when boom, that hits, the next one needs to be falling right then. And so we need a frequency rate fast enough that's going to make that happen. So we're going to try to, it's kind of tough to do. We're going to just regulate this until you think every time you hear a drop hitting, you think you see one ready to drop right there at that point. Because what we can do then is we can give a certain amount of time. I'll just make up a certain amount of time. Let's say we'll do 30 seconds. I could do 30 seconds of time, and we can count how many drops we hear. And so let's just say I did 60 drops, make it easy. So if I get 60 drops in 30 seconds, that is 2 drops per second. That's a frequency. You could call that 2 hertz. But what's the period? The period would be 1 over that, so it'd be half of a second would be the time period. And that would be the time that it took for one drop to fall. So what we could do then is we can put that time, that period, in for the time in our equation and figure out what gravity would be. Now I just made this up, so this data is not important there. Okay, but this is the equation we're going to use, and you're gonna watch the experiment, and we're going to do it two different ways. One way we can try to be a little bit more precise, and you're going to I'm going to start the experiment. You're going to count the number, and I'm going to start a stopwatch, and you're going to count the number of drops that you hear in that amount of time, and then figure out what the period is. So you don't really want to take the drops divided by the seconds. You actually want to take the seconds divided by the drops. So if you have 30 or whatever seconds it's going to be, divided by however many drops you have, that will be the period that you're going to put in this equation so that you can figure out what gravity is in this experiment.
All right, here's our acceleration of gravity inquiry setup. We're going to try to measure gravity today, and we're going to do that by dropping an object a known distance. So the object is going to be little drops of water, and we're going to drop them 1 meter. You'll see I have the meter stick set up here, and up here we have a little spigot. We have a water container. We have a little spigot right here, and I can turn that on and start dropping drops of water, and they're going to fall down 1 meter down, and they're going to hit the aluminum foil. And the reason I have aluminum foil there is that's going to make a noise so that I can determine when I need to drop the next drop. So what I want to do is I can't just drop one drop at a time and try to measure the time. I want to drop a whole bunch of drops at a regular interval, a regular frequency, and then figure out what the period of time is between two drops. So for that, because that'll be the amount of time it takes for one drop to fall 1 meter. Well, the way I need to do that is when I hear one drop hitting the aluminum foil at the bottom, I need the next drop to start falling. So I need to set the burette at the right rate so that I will have, when one drop hits the aluminum foil, the next drop will be starting to fall. So I'll be hearing these little sounds when it hits the aluminum foil, and the amount of time it takes between two of those aluminum foil taps will be the amount of time it takes for it to fall. So I'm going to try to go ahead and set up a rate that I think looks good, and then we'll start a timer, and we'll do like 30 seconds, and I'll let you count how many drops you hear within that 30 seconds. And then if we do drops divided by 30 seconds, or whatever the time is, that'll be the frequency. But what we'll want will be the amount of time divided by the drops, and that will be our period of time interval between between two drops. So I'm going to turn this off for a second. I'll get it started, and then we'll start a stopwatch, and we'll try to count how many drops we hear in that amount of time. Okay, I have a rate set up. Hopefully when one drop is hitting aluminum foil, you can hear them hitting, that the next drop is just starting to fall. That's what that's the rate we need to try to set it up at. We'll see how good a job I did. I'm going to start the timer, and you need to count the drops. And when I say stop, you need to stop counting the drops, and you need to record how many drops there were in the amount of time that we have. So here we go. Ready? Stop. Okay, so figure out how many drops you heard, and if you have to watch the video again, go ahead and do that. Count how many drops you heard from when I started the timer to when I stopped the timer. So if you take the number of drops that you got divided by 30.13, that would be called the frequency. That's drops per second. That's not really what we want. We want the period, so you're going to take 30.13 seconds divided by how many drops you heard hit the aluminum foil, and that will be your period, and then we'll use that period in our equation to figure out what our calculated gravity is. Look down here at the bottom, I have an old tape recorder that I have hooked up, and I have it recording. And so there's a little a microphone on there that if you make some sounds, I can take that through some cords to an amplifier, and then I can put that into the back of the strobe light as an external trigger. You'll notice that it's on external trigger on there. And so what that does is when something hits the aluminum foil, let's see, I'm not sure if we can see it with the light on here or not, but if I make a sound, I don't know if you can see that. Every time I make a sound, it'll flash the light. I'm going to turn the lights off again, so maybe we can see it happening. I'm too far away. I'll do clapping. So every time the drop is going to hit the aluminum foil, it's going to make a flash. It's going to illuminate the room. Now this is going to be helpful because our problem with our last experiment was that we had to just by vision know that if the drop was hitting the aluminum foil, that the next drop was actually just falling from the burette. That's really hard to see that. So now what we're going to do is every time the drop hits the aluminum foil, it's going to flash, illuminate the room, and you're going to be able to see exactly where that next drop is, because it's going to all of a sudden flash and you're going to be able to see the drop. And so what we're going to be able to do is we'll be able to keep the rate going so that you'll see a drop just hovering right below the burette when it goes. So we're going to try to set that up and see if we can get that to work just perfectly. Okay, so there we have it going. I tried to set it up as best I could. You'll notice that the burette, the drop is a little bit below the burette. So here is the bottom of the burette, and right here is a drop hovering in midair. It's not really doing that. This drop falls down, hits the aluminum foil, makes a noise. The next drop falls right into that exact same place. So it makes it look like there's a drop just hovering there, but it's a different drop every flash. So this isn't quite good enough. I want that drop to be moved up to about right here, even with that thing. So I'm going to attempt to do that. So it's going a little too fast. There, bring it up there, it's a little closer. Gotta bring it up a little farther. There. Ooh. That looks pretty good. I want to see what that looks like on the camera. See if I notice it. You can kind of see it. I think we'll zoom in there. We'll see that there's a drop right there on the edge. Whoop. There we go. There it is. Right there on the edge of the burette. Okay. So that means as soon as it hits the aluminum foil, another one's being released right there at the end. Okay, so that's what we want to do. Try to do our timer again and do another 30 seconds and see what that is going to be like. Okay, I'm going to turn the lights on and we'll get you another timer here. Let's see, I guess I'm going to have to zoom out. See, now it's hard to tell again, but you can kind of see it kind of makes a flash on that drop right where it is at that moment. That's kind of cool. I'm going to zoom back out here. And I'm going to give you 30 seconds, so get ready to start counting. As soon as I say go, go. Stop. Okay, so you need to take, the total time was 30.41. If you take 30.41 seconds, divide by how many drops you just counted during that time interval, then you'll have the period of the timer. That'll be T in your equation, and you can try to figure out what gravity is now. See if we get a little more accurate result using the strobe light to kind of help us out. Okay, and that'll be the experiment. I'm going to zoom back in here just a little bit and kind of play around with it a little bit and see if you can. I want to make sure everybody understands kind of what's happening here. So I'm going to set it up here, turn the lights back off, and so you can see that drop is flashing. I'm going to zoom out. So now you should see it down here. Go a little farther down. If I go too fast, now it's clear down here. So that would have been going too fast. If we slow it up, then it'll actually make it look like the drop is going to be going upwards like this. It's not. Whenever this hits, there's another one's falling right in that exact same place. So if I start slowing it up, once that thing hits, the next one will not have got as far. And so it'll look like it's moved up. And then when that one hits, this one will not have gone as far, and so it'll look like it's moved up. So it'll look like the drop is actually moving upwards if I slow this down. So here we go. There it comes up. It's coming up, coming up, coming up. And slow a little bit more. And there we're pretty good, right back. There's a drop right there on the burette. So we're pretty much back at the rate where we were when we just did that second part of the experiment. When that thing hits, when the drop hits, there's another one that's right here in its place. Okay, we'll see how well our gravity measurement came out.